I solemnly swear that I am up to no good.
To begin, we will be using Quidditch to examine the differences between distance and displacement. Distance is how far an object travels, while displacement is the distance between the initial position and final position said object traveled. Now notice how in an effort to catch the Gryffindor chaser, the first Slytherin chaser on the right travels a greater distance around the Quidditch stand than the second Slytherin chaser on the left, who traveled in a straight line. Despite their different distances, they end with the same displacement as they began in the same initial position and ended in the same final position. Next, let's examine the differences between speed and velocity. The speed of an object is the distance it travels divided by the amount of time it travels. Velocity is the displacement of an object divided by the amount of time it travels. Notice how in the simulation the red and green circles travel the same distance, 5 meters, in the same amount of time, 2 seconds, meaning they both travel at a speed of 2.5 meters per second. But notice how the red circle moves in a straight line due east, meaning its velocity is 2.5 meters per second east, while the green circle moves due west, meaning its velocity is 2.5 meters per second west, indicating their different velocities. Finally, let's examine acceleration. Acceleration is the change in velocity divided by the time. This change can include the change in the magnitude of the velocity or a change in the direction of the velocity. Observe the motion map of Harry's movement through platform 9 3/4, where each arrow is proportional to the magnitude of his instantaneous velocity, and each dot represents his position. Harry begins at rest before increasing his velocity, accelerating into platform 9 3/4. Then, after he passes through the wall, he begins to decrease his velocity, decelerating and returning to rest. Notice the different lengths of the arrows representing the changes in his velocity, showing his acceleration and deceleration.
In order to reveal the relationship between displacement, velocity, and acceleration, let's look at the kinematic equation. The first equation tells us that the final velocity is equal to the initial velocity plus acceleration times time. The second equation reveals that the final position is equal to the initial position plus initial velocity times time plus 1/2 of acceleration times time squared. The final equation shows us that the final velocity squared equals the initial velocity squared plus 2 times acceleration times displacement. From these equations, we can derive the missing value, whether it's the initial final velocity, the initial final position, the time, or the acceleration. In order to use the first equation, the problem must not relate to position. As for the second equation, it must not need the final velocity. And lastly, for the third equation, it must not require time. To better understand how the variables of motion relate to one another, let's further review the graphs. From the position time graph, as the slope increases, it indicates that the object is moving in the positive direction. As the slope decreases, it indicates the object is moving in a negative direction. The slope of the position time graph reveals the velocity of the object. The first kinematic equation also could be used to find the velocity. When there are no changes in the position, the velocity is 0. When the position is changing linearly, the velocity is a constant non-zero. As for when the position is changing exponentially, it indicates the velocity is changing linearly. The slope of a velocity time graph reveals the acceleration, and the area of the velocity time graph depicts the displacement. When the slope of a velocity is constant or 0, there is 0 acceleration. When the slope of the velocity is linear, the acceleration is constant. The area of the acceleration time graph indicates the change in velocity of the object. From this card demonstration, we can see that there's an exponential displacement, suggesting that there's a linear velocity and a constant acceleration. To examine freefall, let's look at the example of when Voldemort and Harry Potter fell off the building.
Let's finish this the way we started. Together.
When Harry Potter pushed Voldemort and the two both fell off, the initial velocity was 0 meters per second. As the time increased, their velocity increased linearly, allowing for exponential distance to be traveled. When in the air, there were only one force acting on them, the force of gravity, which also caused a constant acceleration of 9.8 meters per second squared. We can also see such example when looking at the following demonstration. When the Harry Potter book and stuffed monkey were dropped, as soon as they were released from my hands, the only force acting on it was the force of gravity. It can also be seen that despite the mass of the book being greater than the stuffed monkey, it took both objects the same amount of time to reach to the bottom. The only thing that could have changed the time and the final velocity is the height of the drop. The mass, however, does not have any impact.
In this demonstration, we will be showing two-dimensional projectile motion. As shown by this video, increasing the height of the system will result in a greater time in the air and a greater distance traveled by the projectile. This is because the velocity of the ball can be described with two components, the vertical and the horizontal vector. In projectile motion, the horizontal component of the ball remains at a constant velocity. This is because there are no forces acting horizontally, so there is going to be no change in the horizontal velocity. This can be seen in this clip in the Ministry of Magic, where as the prophecy balls are falling off the shelves, it's moving at a constant speed horizontally. However, there is a force acting vertically on these projectiles. As these projectiles fall, gravity is constantly being exerted on it. This will result in a downward acceleration on the ball as the net force is acting downwards. Time is then based off the height because time is based off the y component of the system. We can furthermore derive the equation for time by using one of our kinematic equations. The initial velocity of the projectile is 0 meters per second, so we can cancel that out in the equation, and then we can isolate the variable t in order to get this equation on the screen. Now we will be talking about projectile and arc. Like two-dimensional projectiles, gravity is the only force being exerted on the projectile during its time in the air. There are also two velocity vectors, the horizontal and the vertical vector, and the horizontal component of the velocity is remaining at a constant speed. Now in this demonstration, we will be exploring the effects of the launch angle on projectile motion. As we can see in those videos, the objects drawn with a larger launch angle had greater time in the air, yet a smaller horizontal displacement. The object drawn with a smaller angle though experienced more horizontal displacement, yet less time in the air. We can explain these differences by using a free body diagram. The applied force on the ball drawn with a greater angle has two components, the vertical component and the horizontal component. As we can see in the graphic, the vertical component is much larger than the horizontal component. However, with the other object, we can see that the applied force has a smaller angle in respect to the horizontal and has a larger horizontal component and a smaller vertical component than the first object. As a result, the first object drawn will have a larger vertical velocity after being launched, while the second object has a larger horizontal velocity upon being launched. Because the ball launched with a greater angle has a higher vertical velocity upon being launched, it will take greater time for it to reach its maximum height, as the maximum height is when the vertical velocity is equal to 0 meters per second. As a result, because time is a function based off the y component of the motion, it will take longer for the ball launched with a greater angle to reach the ground. As discussed earlier, the ball launched with a smaller angle will have a greater horizontal velocity and a smaller vertical velocity than the object drawn at a greater angle. As a result, the ball will reach its maximum height in a shorter amount of time, meaning that this time that this ball spends in the air is shorter than the ball which was launched at a greater angle. However, its horizontal velocity was much higher than the ball drawn at a steeper angle, meaning that it can travel a greater horizontal distance, as in every second it is traveling more meters than the other ball.
Mischief managed.